Let's take a look at what I believe is exercise number 46 in the current edition of the textbook. We are given the function y equals e to the negative x times cosine squared x all over x squared plus x plus 1, and we are asked to find its derivative. Now, you can do this using only the techniques of the previous sections. We see that this is a quotient, so you can begin by applying quotient rule. When you take the derivative of the numerator, that's a product, so you'd have to apply the product rule. Each factor is itself a composite function, so you'll need to apply the chain rule for each term in the product rule. You can do it, but it's a little bit unpleasant. The core idea that we introduce here is the notion of logarithmic differentiation, where we can take advantage of the properties of logarithms to manipulate an expression and get it into something that is much more agreeable. So the idea is that we can begin by not using calculus yet. We'll get to the derivative later. And we'll take the natural log of both sides. We'll say that the natural log of y is equal to the natural log of all of this stuff. Okay. And as usual, I will write more steps than I usually do. You want to practice with this probably so that you can do this in slightly fewer steps. Eventually, don't skip anything that's useful, but keep practicing until you are more confident with these things. Now let's look at the properties we have here. We have a multiplication and we have a division. So if we pull this apart a bit, we see that this is the natural log of e to the negative x plus the natural log of cosine squared of x minus the natural log of x squared plus x plus 1, right? Let's simplify these a little bit further. The natural log of e to a power is just that power, so we have negative x. This is cosine x quantity squared, so with the property we have involving exponents and logarithms, we see that that is twice the natural log of the cosine of x. And that doesn't really work out too well. We'll just have to leave that how it is, right? If we could easily factor this polynomial, then we could break that apart into a sum of logs, which would become a difference when we push the negative through. But that looks irreducible to me, so we're probably just stuck with that how it is. So, if y is equal to all of this mess up here, we see that the natural log of y is equal to this, negative x plus twice the natural log of cosine x minus the natural log of x squared plus x plus 1. Now let's differentiate both sides. We'll take the derivative with respect to x at the left-hand side, and the derivative with respect to x of, I don't want to write all that, so I'll just make some ditto marks there. The derivative of the natural log of y is going to be y prime divided by y, right? It'll be 1 over y times the derivative of y, so we have that. The derivative of all of this stuff, derivative of negative x, is negative 1. We have plus 2 times the derivative of the natural log of cosine of x. We will have cosine x in the denominator. In the numerator will be its derivative, which is negative sine x. Now we have minus of the natural log of this thing, so we take that derivative. The argument x squared plus x plus 1 goes into the denominator, and the numerator will have its derivative. That looks like 2x plus 1. So, trying to get the y prime by itself, we see that y prime is equal to, if you multiply both sides by y, you get y times, how do I want to do this? Yeah, parentheses are fine. We have negative 1 minus 2 times the tangent of x minus 2x plus 1 over x squared plus x plus 1. For some purposes, this might be good enough. For many other purposes, you might actually want to write this explicitly in terms of x. So you'll go back to the beginning, the original definition of y, and say, okay, so that is e to the negative x cosine squared x over x squared plus x plus 1 times all of this stuff, negative 1 minus 2 tan x minus 2x plus 1 over x squared plus x plus 1. And if you wanted to, of course, all three of these terms are negative, so you could factor that out to the front, put a negative sign out front here, and make that 1 plus 2 tan x plus 2x plus 1 over blah, blah. Doesn't really matter, but however you want to write that, we have this here. There was a fair bit of writing because I wrote out every single step of the logarithmic expansion. With some practice, you can get to this line in just a step or two. And then once you have that, with enough practice evaluating derivatives of logarithms and also implicit differentiation, it shouldn't be too hard to get down to this step here where we have the y prime over y equals all of this stuff. And then really when we multiply both sides by y, if you wanted to, you could do this substitution in the same line, and then you would just have that. So I kind of wrote about twice as much as was actually necessary to hopefully make things a little bit clearer what I was doing. But you can see hopefully that, surely you can see that this process is much easier and simpler to work with and probably produces cleaner end results than if we were to try to evaluate that derivative directly using, like I said, quotient rule, product rule. That would get kind of messy. Have a bunch of other stuff floating around in there. But yeah, that's the core idea behind logarithmic differentiation, is that we have a situation that probably doesn't even have logarithms. It could, but frequently when there are no logarithms in sight, just knowing what we know about the properties of logs and what they do for us, we see that, oh, hey, if we bring in logarithms here, that'll allow us to separate this thing out. It'll turn complicated expressions into much simpler expressions, right? Logarithms turn they turn multiplication and division into addition and subtraction. They turn exponents into multiplication. That makes things a whole lot easier to work with. So bringing logarithms in allows us to kind of shift this into a different space where derivatives are much easier to compute, and then we can just translate back at the end, which really just amounts to multiplying that y over, because for the most part, the implicit differentiation takes care of things on its own.